Yeah, welcome back. We will now talk about linear classifiers. Yeah, classification is maybe the central task of pattern recognition. For example, in a setting in biology or in robotics, sensors supply information about an object, and one needs to decide to which class the object belongs to. Is it a cat? Is it a dog? Is it a person? And based on this class assignment, an agent might act differently. If it's a tiger, maybe the agent tries to hide. If it's something to eat, it will react differently. The nice thing about machine learning is that a few model classes like neural networks, kernel approaches, and so on can be applied to almost any supervised learning task. But this hides a bit that the data settings can be quite different. So we have inputs and outputs, and we train a neural network, and we might get good performance, but the data situation can be quite different in different situations. No? For example, there are problems where class boundaries are well defined, but maybe quite complex. An example is optical character recognition. So here deep neural networks and manifold learning in kernel systems are quite effective. So because the boundaries between the classes might be quite complex, but there's little noise on the data in the sense that a human in, let's say, 99% of all cases can give the correct label. So this is the situation where we say the classes are separable, but the class boundaries might be quite complex. And that's why we also made these distinctions between cases 1, 2, 3, and 4. In other applications, there's little structure in the data and classes overlap. This is the situation, for example, often encountered in healthcare applications. So every input has, or many inputs have influence, but maybe weak influence. And the outputs are not always unambiguous. So you give the same medicine to different people, to different persons, and the outcome might be different. So that's not so much the issue of finding a very complicated class boundary. The issue is more of is there a positive effect of the medication and of the treatment, and how large is that effect? So is there a signal at all? Is the medication, does it have a positive effect on the patient in terms of fighting the disease? And maybe then also determining for maybe which subclass of people, which strata, it's called in healthcare, the medication might have different effectiveness. No? So maybe age relevant or gender relevant. We are talking about linear classifiers, which separate classes by a linear hyperplane. And in high dimensions, a linear classifier often can separate the classes, but it cannot solve the exclusive OR problem, which is a complex function in low dimensions. But in combination with basis functions, kernels, or neural networks, linear classifiers can also form nonlinear class boundaries, as we have discussed. So sometimes you can think of the linear classifier, or what we are discussing today, as being the last layer in a deep neural network. In other cases, it's really a linear classifier applied directly to the inputs. Yeah, and we have seen these pictures before. So we have inputs with different weights on them, W0 to Wm. And yeah, so we are calculating the activation, the inner product of X and W, or the weighted sum of the inputs. And then we might apply a binary threshold function, which then the output might be -1 and 1 or 0 and 1. Or we apply sort of a null network type of transfer function. In that case, so here in the sigmoid, we might interpret the output as a probability that a certain class is true or false. The class is true or false. And we've learned about the perceptron with the sign function, or the sigmoid function, or the SIG, this logistic transfer function. So we will focus on binary classification, where the task is to assign binary class labels, so 1 or 0 for the two classes. So if I belongs to class 1, yi will be 1, and in the other case it will be 0 in the training data, or in other cases we use the label 1 and -1. And we have essentially learned about the perceptron, and now we'll learn about additional approaches. And we start with generative models for classification. That might also give you some sort of a glimpse of how generative models can be used in machine learning. And the second one is logistic regression, which gives you the cross-entropy cost function, essentially. And then the third case, classification via regression. Yeah, so just to remind you, this is a case where two classes are linearly separable, and we want to find some reasonable hyperplane which separates these two classes. This is the case where the two classes cannot be separated linearly, and in this case maybe you want to apply basis functions on neural networks to get the job done. The class boundary is complex, but the classes can be separated. This is the classical example which we have discussed, where the two classes cannot be separated. You cannot place a linear hyperplane here anywhere that would separate the greens from the reds. But and this is something important also to learn. Separability is not a goal in itself. So here in this case we have again the two classes. But as I sort of indicate, is that the two classes are separated, are generated by maybe Gaussian shapes distributions, or in the extreme case, like a uniform distribution for the green case in this sphere here, and a uniform distribution for the red class in this red circle. And the data simply overlap. So there are some input data which can belong to either class. The classes are simply not separable based on this simple information I'm having. And so in this case it doesn't make sense to try to go to a basis function space or use a neural network. In this simple case, this blue separating hyperplane is optimal. although it doesn't separate the classes, the training data, and it will also not perfectly predict the labels in the test data, but it's not because the classifier is too simple, it's because the classes cannot be assigned uniquely to either class in this region. Sometimes people also talk about noisy classification problems. And they occur a lot. For example, in healthcare, this could be healthcare data. If you're trying to fit or find a classifier which separates the classes, it's not very helpful because you're essentially fitting the noise in the data. So we are starting with the idea of generative models for classification. So in general, in a generative model, one assumes a probabilistic data generating process. So you can think of this as a likelihood function. So you have an explicit model for the likelihood. Before we typically modeled the probability of the class given the input, and here it's the other way. We are modeling the input given the class. And you can be quite creative and quite problem specific here, and assuming, based on your assumptions of how the data is generated, these generative models can be quite complex. We will only consider the simple case here of a Gaussian distribution. So the data is generated from a class-specific Gaussian distribution. Another thing we have to model is the probability that a class occurs. So if y equals 1 stands for good customer and y equals 0 stands for bad customer, then P of y would give us the probability of good customers versus bad customers. So, and this can often be simply estimated based on the available training data, or you have a good guess about that. So that's not so difficult. No, that's just, in our case, one number. Because the other probability is 1 minus that number. So very simple. And then, and this is then more complex, we have to model how attributes are generated. That's why it's called generative model, given the classes. Now, so you think of like maybe nature generating something. So we use this tilde here because we don't consider the offset, the input with a zero, with a constant input. No, we don't take that. We only consider the real attributes. And so X tilde could stand for income, age, and occupation. And given that a customer is a good customer, so a good customer might have high income, might be whatever, not too old, not too young, might have some interesting occupation, and for another good customer, so I'm just making this up and nothing meaningful behind it, maybe low income, too young or too old, dangerous occupation or something like that. And so we need this P of X tilde given y for the two cases, y equals 0 and y equals 1. And then we can simply apply Bayes' formula to give us what we are really interested in, the probability of a good or bad customer given the attributes or we have about the information we have about the customer. The probability that a given customer is a good customer or a bad customer, given what we know about the customer. Then this might be for credit assignment. Not credit assignment, for giving out a financial credit, for example. So we just give these probabilities some names. So the probability that y equals 1 is kappa 1, and the probability y equals 0 is 1 minus kappa 1. and this number should be between 0 and 1. So this is the idea how the data is generated. And in the next step, a data point has been generated from this distribution. And we don't consider this the constant input or the xi0 input. So this is the x tilde I, for I being the customer or something. And now we have a complete model. So we have what we like in a Bayesian approach. So we have P of y and we have P of x tilde given y. And there's a subtle point. So now we are applying a Bayes formula, and we have a complete model here, but we don't necessarily put a Bayesian prior on the parameters. So that is what we discussed before. In Bayesian machine learning or Bayesian statistics, you also consider that. And this is not the point here. And the point is here that we are modeling explicitly P of y and P of x given y. And then we simply apply a Bayes formula. So this is, we assume that we have an estimate for this one, the probability of the attributes given good or bad customer, the probability of good and bad customer, and this is then a normalization, which can be calculated in this way. So P of y equals 1 times P of x given y equals 1, and plus P of xi given y equals 0, and times pi of P of y equals 0. And so this is just the calculated by this marginalization operation. So that's the solution. And now we just have to think about how this term is modeled here. Oh, here's also something maybe illustrative. So this is from Duda-Hart, pattern classification and scene analysis. And this is from the first edition, which is where a lot of people in the early 90s learned about statistics. Because a lot of people sort of came from other fields, invented neural networks and backpropagation, and people like me wanted to understand a little bit better what is going on, and others like Michael Jordan. So this was the Bible at that time. And personally, I prefer the first edition, which is the Duda-Hart, and then there's a second edition, which is probably easier available. I think Duda-Hart and Stork. It's probably also a good book, but it's something, if you learn it by one book, you sort of stick with it. So here it's about ashes and birches. So ashes are German Eschen and birches are Birken. And maybe you have a sensor which measures the brightness of the wood. So there's dark wood and bright wood. And there's only one input, so this is the only input. And then people maybe are modeling these distributions. So let's say ashes are darker on average and have this distribution. So maybe it could be a Gaussian distribution, although it looks a little bit distorted. And here's here's a distribution of the probability that a birch has a certain brightness value. So it is brighter on average, but there are also some dark birches with a dark wood, and then there's some birches with a really bright wood. And now you get the sensor information for a new piece of wood, and you want to decide based on this one sensor information, is it birch or is it ashes? So these are the P of x given y. So for y equals 1, ashes, for y equals 0, birch. And whatever, maybe they have the same probability in this sawing mill or something. So and then, but this is what you have to plug into these formulas, and this normalization is not so harmless as it might look first, because if you look at these posterior distributions, the probability that it's ashes is this one. So if it's a dark wood, it's very likely that it's ashes. And then if the brightness is higher, it's much more likely that it's a birch. And then here's maybe a transition point where the probability of birches becomes larger than the probability for ashes. So if you're forced to make a decision, then maybe you're using this point. But of course, if there are different costs assigned with misclassifications, you might also pick another point to make the decision. So here, if you look at this a little bit, I think it becomes clearer what is going on, and also that the posterior can have so the sums have to add to 1 because it has to be one of them. And due to this normalization, you get this very different shapes from the likelihood models. Although if you look at a certain input, the proportions you can also read off from the likelihood model in cases the classes have the same probability. But probabilities have to add to 1. So that's why if you add these two curves here, you would get a constant. And we want to learn from data. So as I said, this probability of y equals 1, which is our estimate for kappa, is simply the number of times we have observed class 1. So n1 divided by n, where n is the total number of training data. And the other number is then simply 1 minus kappa 1. So this is just a proportion of observations. Very simple. Yeah, and for this likelihood model, you can choose an application-specific distribution. So remember, this is the likelihood. And maybe you say, okay, maybe it's not quite a Gaussian. There's also the question, how did they observe, or how did they get this function? But maybe if you don't have too much data, not too much data, maybe a Gaussian approximation would be quite good. So you just assume that these two likelihood functions are Gaussians. And we are right away going to the multivariate case. So x is a vector. Before in this example it was just one scalar. And and we are assuming the class-specific data distribution or feature distribution is a multivariate Gaussian. We already have learned about it. It's specified by the mean, or it's also the same as the expected value, or and a covariance matrix, right? So if we explicitly write it, it's 1 over 2 pi to the power m divided by 2, where m is the number of features, the square root of the determinant of sigma, and the exponent, and in the exponent we have minus 1/2. The difference between the data point and the mean value. This is a vector. We take the transpose. The same vector is here without the transpose, and then in the middle we have the inverse of the covariance matrix. And this is works often pretty well, even if the Gaussian assumption might not be extremely accurate, particularly in high dimensions. So we looked at multivariate distributions already. So this is a Gaussian distribution in 2 dimensions. So the main axis might not be aligned with the coordinates here. These are the projections, or the marginals on the 2 dimensions. Maybe as expected, or here's another pretty picture. And the solution is it's not very complicated, but I'm not showing you the derivation, but it's the outcome is as expected. So so the mean value for class L, so L is 1 or 0, is 1 over the number of training data points which belong to class L, and then the sum over all data points or attribute values which for the data which belong to that class. So that's sort of intuitive. You just take the mean of the data which belong to the class. And now there's something special. Maybe let me show you. Yeah, so what I showed here, so mu, so the center, is of course class specific. So the two classes have different centers. But I don't use the superscript L here for the covariance matrix. So we assume that the covariance structure is the same in both distributions. Again, it's probably not true. Why should the two distributions have the same covariance matrix? But it works very well often, and that's a very common assumption. And that's why we only have to estimate one covariance matrix. So it's 1 over n minus m. N is the number of data points, m the number of inputs or features. And this is this famous correction to get an unbiased estimate. And then you sum over both classes, you sum over all data points. You take the difference of the data points with respect to the particular class mean. So if this data point belongs to class L equals 0, then you have to take the mu0. If it's 1, then you have to take the mu1. So you consider the mean of the class to which this data point belongs, and you multiply it. So this is now the transpose is on the right side and the vectors on the left side. Remember, this gives you a matrix, and this is how you can calculate an estimate of the covariance matrix. So now we are I'm showing you a few identities which we will need in a second. So first of all, if we look at this quadratic term here, that's this one in the exponent here, we can just multiply crosswise, and so we get a term of x sigma x. That's this one here. Then mu sigma mu, that's this one. And then 2 times the cross terms, x sigma inverse mu and mu sigma inverse x. And this becomes, without the 1/2, the mu L center transposed inverse of covariance matrix times xi. So that we are just multiplying out the terms. And we can do the same thing for the difference of 2 quadratic terms with the same covariance matrix. So we have the same x, but we are considering mu0 and mu1. And if we consider this term and multiply everything out, we get this expression here. For the left one and this one for the right one. And then these two guys here, they cancel out. And we can write the result as a difference of the mu vectors transposed inverse of the covariance matrix times the x vector. So this is the only term which depends on xi. And then a term which only depends on mu0, and a term which only depends on mu1. And so this already looks like a linear expression. There's some offset here, then w0, and here we get a linear term. Because now we are interested in the a posteriori distribution. So for example, the probability that y equals 1 given x tilde. And by base formula, we know it's p of x given y times p of y divided by the sum of these two terms for the different assignments to the classes. And then we divide this expression simply by the nominator. Then we're left with a 1 here. This divided by this gives the 1. And then we have this expression over here of the p of x given y equals 0 times probability of y equals 0 times divided by the probability that x given y equals 1 multiplied by the probability that y equals 1. And so we have the 1 and the 1, and here we are now, these are the likelihood terms, these are the prior terms. And now we have two Gaussians and not the product but the quotient, which means that we take one Gaussian and subtract the exponent of the other Gaussian. No? And that's why we just calculated this stuff here. So we get a term here now, which is only dependent on x. That's the only term. And we get a term which only depends on mu0 and a term which only depends on mu1. And we just write this because you know that this is a logistic function, 1 over 1 plus e to the something, or e to the minus something. So we can write this as a sigmoid applied to w0, some offset, plus the inner product of x and w tilde. Or if you want to write it as a sum in this form. And now we have to identify these terms from this expression. And now we have to consider the linear term, which gives us the w tilde term, which is the inverse covariance times the difference of the mean terms over here. No? So this expression here. And everything else becomes the offset. No? Now here's recall, that's how the sigmoid is defined. 1 divided by 1 plus e exponent of the negative argument. W tilde, I guess w tilde is independent of these prior class probabilities, which will be later important for case control studies, but it's a minor point here. So this is an interesting result, and then the W0, as I said, is a collection of all the other terms, including the log of the of kappa 1 divided by kappa 0, because we also have to put this into the exponent to be able to use this identity with the sigmoid. So e to the log of this is also will be in the exponent, and that's why we have this term here. And here, of course, the class proportions are reflected, so that they play a role, just not in the linear terms. So you can think of this as also finding a plane where the projection on this plane, the classes are optimally separated. So to wrap up the story, so we assumed the likelihood functions are multivariate Gaussians with the same covariance function, and then we can estimate these parameters, and the discriminant function we can write as a sigmoid function. No? And this might be one motivation why this logistic regression function is not just something by accident because it looks nice. It has several interesting interpretations, and the one here is that it's the posterior probability distribution for the classes when we make these assumptions about the two Gaussians. But also note, we don't only get class boundaries, we get probabilities. So our model will give us the probability for a given input that the true class is 1 or 0, and then maybe the application needs that information. It doesn't just want a decision, it also wants to have these probabilities Now, if these probabilities are both more or less equal, then you know that your classifier is pretty uncertain. And if the classes are pretty clear, either 1 or 0, you know that your classifier is pretty certain. Yeah, for the experts, there's also something called Fisher linear discriminant analysis, or LDA, where one projects the data into a space in which data from the same class have small variance and where the distance between the class modes is maximized. And it turns out the solution is exactly the same. It's a different starting point, so this is an optimization criterion, but the solution is exactly the same. Yeah, and here I make this point again that we use Bayes formula, but it doesn't mean that the parameters, the mu and the sigmas, are treated in a Bayesian way. So it might be a little bit confusing. Bayesian statistics typically means the parameters are also treated as a Bayesian random variable, and this doesn't have to be the case here. We can do likelihood estimation for the parameters and still apply Bayes' formula. So that's not a contradiction. But of course, we could also do a Bayesian treatment of the parameters. It would just be a little bit more complicated. Yeah, you might think this assumption that these two sigmas, these two covariance matrices have the same shape or are identical is a little bit artificial. If you have good reason that this is a bad assumption, you can of course also approximate them with different covariance matrices, and this is absolutely okay. I mean, the boundaries will not be linear anymore, so the decision boundaries, they can be typically they have some hyperbolic shape or elliptical shape, and so if you have good reason that this is a good assumption, no problem with that. In practice, it turns out it often leads easily to overfitting, so people often stick with this assumption. Yeah, I mean, the generalization to multi-class is also straightforward. You just simply estimate a different Gaussian for each class and apply Bayes rules without shared covariances or not, or with shared covariances or not. So you can, in our example, we have estimated 2 Gaussian distributions. You can also estimate 10 Gaussian distributions, one for every class, and then you can build a classifier for digits, for example. Yeah, sometimes this is called generative discriminative pair. So here we have a Gaussian analysis with a shared covariance matrix as a generative model, and so that would be the generative part, and then logistic regression as a discriminant model for the discriminative part. So so far now we said the 2 Gaussians, they're multivariate, but they have a full covariance matrix. So there's don't assume any special structure in the covariance matrix, but we can simplify that, and this leads to the so-called naive Bayes classifier. So we assume still multivariate, but that we can write the Gaussian as a product of simple Gaussians, of one-dimensional Gaussians, which essentially means that the covariance structure in the multivariate situation, the covariance matrix would be diagonal. If it's diagonal, we can write it as a product of Gaussians. So still they have different means and maybe still attribute-specific variance. So now we write this as sigma square j. So this would be the diagonal term in the covariance matrix sigma. And now we, of course, the number of parameter is considerably reduced. Of course, we have to still estimate the mean, but instead of estimating a covariance matrix, we only have to estimate the diagonal terms in the covariance matrix. So it completely ignores class-specific correlations between features, and this is where the term naive came from. But again, it's oversimplifying, but it often gives good results in cases we will discuss. So I think that's even a worse name for it. I don't remember. Naive Bayes is pretty bad enough. So and even more naive, if you want, is that all Gaussians have identical variance. So it's not sigma j square; it's sigma square. So it's the big sigma, the covariance matrix would be a unit matrix multiplied by sigma square. And then we can calculate, so this would be wj, so for the jth input is 1 over the sigma square, and the difference of the means of these for these two classes, and w naught assumes this form here. So essentially we can, at least wj, so the proportional parameter is independent of the other inputs, and we can calculate that right away without considering all the other inputs. W naught depends on all dimensions, and the smaller the sigma, and the sharper the transition between these two classes. So this is called naive Bayes classifier for the Gaussian case. And there's also corresponding naive Bayes classifier for other distributions. So here we are considering the Bernoulli naive Bayes classifier, which means that features are 1 or 0. So they have been popular in text analysis with often more than 10,000 features, so 10,000 keywords we are considering in a text. So for example, the classes might be spam or no spam, and the keywords, the features of the keywords in the text. And then, we wouldn't assume a Gaussian distribution, but a Bernoulli distribution, which essentially just means we're considering the proportion of the two cases. So, for example, the probability that the word J occurs in an email, given that it's a spam email, would be this gamma parameter for J and spam. So it's the probability of observing word J in the document for spam documents. Yeah. And 1 minus this number would then be the probability that it's not occurring in the spam email. And then we also have to consider the other cases. So the word does not occur. Spam is just 1 minus this number. Then the probability that the word occurs in a no spam email. So here we have this n subindex here. And then 1 minus this number would be the probability that the word does not occur if it's not a spam. So we have these 4 cases. But it's sort of word specific. No? And then we also make this naive assumption that everything is sort of attribute specific and independent, so there's no dependency between these spam or no spam words. And then we get this formula. Also we're calculating the posterior as before. So here we have the kappa spam, and kappa non-spam would be 1 over 1 minus this number, sorry. And then we multiply here in the denominator over all words. So here this just means that if the word occurs, then this is 1, and this term is left over, and this one disappears. And if the word does not appear, then this one survives, and we multiply it, or we have this remaining term. So this is just a convenient way of distinguishing these two cases. And then we have the same term here and the same and the opposite term over here. And now it almost looks like a sigmoid. And again, we are dividing by this nominator. Then this is the 1, this is the 1, and this is a quotient of two terms. And we again get a sigmoidal behavior, where we get an offset and a weight for every word. And this Wj is the difference between the logs of these gammas for spam minus non-spam, and a minus log of 1 minus gamma minus log of 1 minus gamma for the spam and the no spam case. And we also get an expression for this W naught. Yeah. So here's another generative discriminative pair. So the Bernoulli naive Bayes classifier and logistic regression also have this properties. Yeah, so in all these cases we sort of designed an interesting or problem-specific likelihood model, the probability of the observed data given the two classes. And then we have to estimate these class proportions, which is of course very simple, and then we apply Bayes formula to give us the posterior classes. And this principle can be applied to more complicated distributions, and even for distributions with latent variables in a hidden Markov model, for example. So we have a good motivation for this sigmoidal function for the posterior probability for the classes. And now we will learn about different other motivations for the sigmoid. But first, it's we just make this assumption that these posterior distributions, probability of y equals 1 given x has this particular shape, but we don't estimate these w's based on these Gaussian assumptions. We are just optimizing this as our cost function. So the likelihood function is the product over all data points times the sigmoid of this linear expression to the power of wi times 1 minus sigmoid of this expression to the power of 1 minus y. And this term survives if the target is 1, and this one survives if the target is 0. So this is just a convenient way of considering these two cases. And this is the product over all data points. Then we are considering the log likelihood function, which is the log of that expression. And so we have to consider that this can be expanded into 1 divided by 1 plus e to the minus this expression. And then we get the log. First we leave the log, the sigmoid as it is. So we have the log of the sigmoid, but the log of this is y times this expression. So this is what we are seeing here, and the log of this expression is 1 minus y times the log of this expression. So that's what we are seeing here, and this is the same as the negative cross entropy cost function, of course. Now we are substituting the exponent for the sigmoid, so 1 divided by 1 plus e to the minus input this place over here, and we get, for this expression, we get this term over here. And then we write this expression, so log of something to the power of -1 is minus the log. So we can get rid of this fraction over here and over here as well. So we get minus the sum over yi log of 1 plus e to the minus argument plus 1 minus y times log of 1 plus the exponent of the argument. Then we are calculating the derivative to get the gradient, and so we have to take care how we take the derivative of the log is 1 over the argument times the derivative of the inner of the argument. So then we get this is 1 over the argument, and this is the derivative of this expression with respect to the argument. And same over here. And then we recognize that this is so we can divide by normalize it or divide it by this expression over here, and then so the exponent. Then we are left with yi times xi times 1 minus sigmoid of the argument minus 1 minus y times x times the sigmoid. So we have to make these identifications over here, and so the gradient is then the difference of the sigmoidal output and the target times the input. And then of course we can do gradient descent optimization, or traditionally people use something like a second order method like Newton-Raphson optimization, but that doesn't really matter for us. Nowadays, of course, gradient-based optimization is extremely popular, so we would probably use also stochastic gradient descent. So if we have only one input, we've seen this before here, maybe we have target 0, so the class is 0, class label is 0, here's the class label is 1, and we get this sort of smooth transition between these two labels classes, and so it's not like a abrupt transition as in the perceptron. So here is another derivation of the sigmoid, which I think in a way I like it best, because it can also be generalized to other cases. So we are starting with a Bernoulli distribution of the class labels, and Bernoulli just means that there is a number for that the probability is 1, and 1 minus this number that the probability is 0, and this parameter theta is between 0 and 1. And this this is sort of an awkward constraint, no? Because if you do gradient descent, I mean, how do you take care that this theta doesn't become larger than 0 or less than 0 or larger than 1? So in this, there's this sort of trick in the theory of the exponential family of distributions. We just substitute and we just say this theta can be written as a sigmoid of eta. And then eta can be any number, between minus infinite and infinite, because the sigmoid always squashes it between 0 and 1. And this doesn't, I mean, the likelihood is not, so the maximum likelihood estimates will be the same because it's a monotonous deterministic transformation. And then we get probabilities, so if you think of these as probabilities, for any eta for any real eta. And this eta is called natural parameter, and this the sigmoid is called the inverse parameter mapping for the Bernoulli distribution. And now we are saying this eta becomes a linear function of the inputs, and this is then what is called a generalized linear model. So we arrived at this conditional probability, class probability, by these arguments. So we first say the output is sort of a class probability, and we have this one important parameter theta, but theta is has these awkward constraints between 0 and 1. Then in the first step we sort of transform it in a way that we now get for any eta we get a valid theta and valid probabilities, and in the next step we make this eta, the natural parameter, input dependent. So in this interpretation, logistic regression is the generalized linear model for Bernoulli likelihood model. And maybe yeah, I mean, there's a very rich sort of theory or behind this, or this can be, as I said, expanded to many other probability distributions, multinomial, but also survival, gamma distributions, whatever. So and these distributions for which this is possible, they form this exponential family of distributions, and so it's if you want, I mean, for example, the statistics institute here in Munich has done a lot of work in this direction. Fahrmeier and Tutz and others. So they use this a lot, and this is just on 2 slides, maybe the simplest variant of this, and gives you a little bit glimpse into this way of thinking. And of course then we cannot just put a linear model in here, we can also put a whole neural network in here, and this is so then the sigmoidal transfer function becomes the output transfer function in a neural network with a cross entropy cost function, and then it becomes also a powerful nonlinear system. So it's very easy to move from a generalized linear model to a neural network or deep neural network system. Okay, and this idea of generalized linear models can also be applied easily to multi-class problems, which leads to the softmax output activation function. So now we are considering what is called a multinomial distribution, which just means that the output can assume or represent several classes, but only one class is true. So, for example, if you have a digit classification problem, you have classes from 0 to 9, but only one of them can be true, can be the ground truth. So if it's a 2, it's not a 3 in the ground truth case. So we assign a theta c to each class. This theta c should be larger or non-negative, and they should sum to 1. So they should form a probability vector, if you want. And C is the class index, and capital C is the number of classes. Now then we do the same thing, so we need to get some reparameterization that the sum is 1, and everything, all these thetas are larger or equal 0. So these are then valid probabilities. And the way to do that is you write this as an exponent of a natural parameter, which is class specific, and you divide over all these exponents for all classes. So in this way, you have a non-negative number, because this is a non-negative number, this is a non-negative number. And if you sum over all theta c's, you will get 1, no? Because you're dividing by the sum over all these exponents. And now again, these eta c's can be unconstrained. They can be any number from -infinite to infinite. And this is then called softmax function of this eta parameter. So this is a vector now, and we are evaluating it at the C component. Then again, with a generalized linear model, we simply say this eta parameter is a linear function, and then we get this expression here, the exponent of the linear function divided by the sum of the exponents of the linear functions for the different classes. The negative log likelihood, so the cross entropy for the softmax, is minus sum of all data points, then the sum of all classes, the target class times this expression, and this of course only survives for the class for which the label is 1, so for which the label is true, and this then the sum over this normalization factor here is then becomes minus the log of this sum of this exponent. And if you take the gradient, you end up with this product of the label and xij, so this only survives for the true class label for this data point, and then you get this expression, xij times the exponent of this input function here with the normalization. And if you then take the gradient, and this is the gradient, if you stochastic gradient descent is then the old w plus eta times xij times yic, so this is 100 minus, and this is again, you have the x here, this is again the softmax function over here. And this is now compared to the Bernoulli case, the only change is that instead of the sigmoid here, we have the softmax. Then, so now we are done with the sigmoid, at least for a short time. So the simplest way to do classification, of course, is simply to treat it as a regression problem, which means essentially we're doing least squares regression on the linear function. And we know how to do that. Now that's I mean, the only difference is that the targets are 0 and 1, and not don't assume any number, but we can still calculate the regression parameters. We have seen this many times before, and then we just assign so to class 1 if it's larger than 1/2. Or if it depends on the labels. And sometimes we have 1 and 0 labels, or 1 and -1 labels, and then the class decision boundary will be differently. Let's look at this example. So if there's only one input or very few inputs, and you're applying this regression idea to the inputs, I mean, it might still work very well, but of course it has some strange properties. So the output can be larger than 1 and less than 0. So, but in high dimensions, and if you, or let's say you work with basis functions or in high dimensions, so if you have these Gaussian basis functions, then if these are the targets with label 1, these are the targets with label 0. This might look quite okayish. No? So there's no guarantee that this doesn't get larger than 1 or smaller than 0, but it typically behaves quite well. So this has been used a lot in the past. I think nowadays people don't use it that often anymore. But to get a quick solution without stochastic gradient descent, if you just want to have one line of MATLAB or Octave or whatever, and just see what kind of results you're getting, then using this is really not bad. But now it turns out that if you do the proper thing with a sigmoid or a softmax, typically the results are slightly better. And also, it's very fast, and regression is often used in statistics and medical statistics to model the treatment effect, because it has also certain advantages in terms of interpreting the parameters. So it's not that nobody's using it in medicine, although they also know the outcome should be either success or failure, so 0 or 1. If the problem is pretty noisy, the assumption that you can model this also with a linear model and least squares regression is quite reasonable, and then sometimes the interpretation of the parameters is simpler in this case. So now let's discuss a little bit how logistic regression is used in medical statistics and why it is so important there. So it's one of the most important models or tools in medical statistics to analyze the outcome of treatments. For example, a new medication, or to evaluate the effect of preconditions like gender, age, smoking, environmental effects. So it's an important task here is to distinguish between correlation and causation. Of course, we can do a whole lecture on causation, but we don't do it. So in epidemiology, the output y equals 1 means that the patient has the disease. So that's a little bit different from clinical situation. So here in epidemiology, you want to find out if smoking causes cancer or some other environmental factor have an impact. So let's say the first real input, so x1 is 1 if the patient was exposed. And this could be a genetic variant, smoking, or an environmental factor. And x1 equals 0 means that the patient was not exposed. And the other inputs are typical confounders, age, sex, maybe other things. So, the general rule is, which is not 100% safe, but pretty safe, in case you have doubts, one should consider all inputs being those variables which might have an effect on the outcome and on exposure. So something which might make people smoke or non-smoke and might also have an impact on that they have gotten cancer. That would be considered so-called confounder. And some people say the more the better. So if you leave one out, it can be dramatic. If you consider too many factors, it's not that dangerous. Although it's also not 100% safe. No? You should definitely not include something which is a consequence of a decision. No? So it's a little tricky, but in general, forgetting a confounding variable can really ruin your experiments, and if you add one too many, it probably doesn't hurt. So here's our logistic regression model, and we are interested in W1, so because that's the one which multiplies with x1. So if W1 is 0 or close to 0, then maybe we say this environmental factor doesn't have an impact on the disease. But if it's significantly larger than 0, then the exposure was harmful. And in this type of analysis, we could also remove the sigmoid. That's what also a lot of people are doing. They're doing linear models. And then again, W1 has this interpretation, and also in a linear model, the influences are independently acting on the output, so that has some advantages on its own. But the sigmoid, or the logistic regression, can be applied in a very important case. So for model fitting, we need data from individuals where we randomly chosen, where these individuals were randomly chosen out of the population. So we should pick random people and then check if they were exposed or not exposed, and then check if they got the disease or did not get the disease. And if this is possible, that's fine, but often, in particular for rare diseases, this can be a problem. If the disease is only 1 in 1,000, then you need a pretty big sample to get like relatively good estimates of all the parameters. No? Oh yeah, and the other case, so this was epidemiology. So you want to understand the causes of a disease. And in a clinical setting, you're more interested in the evaluation of a treatment or of a medication. So x1 equals 1 might mean that the patient received the treatment, and x1 equals 0 means that the patient did not receive the treatment. And y equals 1 might mean that the patient is cured after the treatment. And also, of course, we want to have a W1 larger than 0, then we know that the treatment has a good effect. Yeah, by the way, we don't need necessarily additional inputs. So we don't have to model regression in a way. If we pick, if we assign these treatments randomly. Because then by definition or by construction there is no confounder, and because there's no variable which influences your decision to give the treatment or not to give the treatment, and that's why these so-called randomized clinical studies are so important, because they are insensitive to confounding factors, and because you're sort of rolling a dice or throwing a coin. And the outcome of this random experiment determines if a patient gets the treatment or not the treatment. And assuming that the coin is fair and cannot be manipulated, this assignment is random. And then we don't even have to consider any inputs necessarily. Maybe for other reasons we might, but not because of the statistical problems of confounding factors. So, okay, in both cases we ended up with these sigmoidal functions. And now we are sort of getting to the point why the sigmoidal, or the logistic regression, is so useful. And we have to first define a few things. So the odds for a patient with property xi is defined as the probability that the outcome is 1 given this property, divided by the probability that the outcome is 0 given that treatment. So it's just writing a little bit differently this probability result. For logistic regression, the log odds, so it's here's the definition again, and then we plug in the terms from the logistic regression. So this is the sigmoid, this is this one, this is this term here. Yeah, so we just plug in the expression here. And this is then simply the log, so some terms cancel here, of e to the minus the input, and then the logs and the exponent cancel, and we're left with a negative. So the negative also disappears, and we get the linear term. So that's the first interesting results. If based on our model we are calculating the log odds, then we are left with the linear function without the sigmoidal transfer function. And of course, the linear term here, the input is also called, or not so called, but it also has a particular name. It's called the logit. So now we have the log odds. Now we are going one step further. We are considering the log odds ratio. And that's OR. OR is the odds for that the treatment was given divided by the odds that the treatment was not given. And the log of the odds ratio is then the difference of the logs of these two terms. So log odds ratio is the log of the odds minus the log of the odds for non-treatment patients. And if we calculate this, the log odds, when the odds is this linear term, so we simply multiply, take the difference where we leave everything identical, only that we change this one input. So in other words, the log odds ratio for logistic regression is exactly this term W1. And again, if the W1 is significantly non-zero, then the exposure treatment has an effect. Okay, so you might still wonder why this is important. Maybe it's a cute thing. But there's one important thing which hopefully comes now. Yeah, exactly. So this is again this case of rare diseases. So this is epidemiology. Yeah, this is an epidemiological case again. So we want to consider the cause of a disease. But rare diseases might only affect one person in a million. So if I collect data from 1 million individuals, which is a lot, so every 80th person in Germany, I might only have one individual with a disease, so that's not very promising. So it's easier to collect people who have the disease, for example, breast cancer or another form of cancer, and then collect 1,000 individuals who do not have the disease. And this is sounds a little bit dangerous if you have a little bit understanding of a statistical analysis. No one should ideally pick patients randomly and then look at the properties. And here we are doing sort of a particular design. We are picking, let's say, 1,000 individuals who have the disease and 1,000 who do not have the disease. So it looks like in the selection process we're looking at the target or the output, and that's a little bit dangerous. But fortunately, and this is really the strength of logistic regression, if the individuals in both groups are very similar, so for example, I mean the two groups should not be very different, then of course this can be a problem. And then if we look at the W1 obtained in logistic regression, then the log odds ratio is insensitive to the class proportions. So in this case it means that if we do the selection based on this recipe, and we're doing a logistic regression analysis, we get the same W1 as if we would have done the correct thing of picking randomly people and looking at their properties. So that's why that's the reason why logistic regression is so important, particularly in epidemiology. But in treatment evaluation, it has also very favorable properties. Yeah, so implicitly we have talked about causality here, and this is of course extremely important in epidemiology and in treatment evaluation, and one of the central and extremely important concepts is that of a confounding variable. So confounding variable is a variable which influences both the output and also the assignment to treatment or not to treatment. So that's why if in a clinical study you assign patients randomly to treatment or non-treatment, then the influence of any variable on disappears. So it because it doesn't select, it doesn't have an influence on x1, so there cannot be any confounders. For example, the famous statistician Ronald Fisher, which made amazing contribution statistics, but was also a little bit difficult personality, it seems. And he was a heavy smoker, and I think he also got funding from the tobacco industry. So he argued for a long time that there might be a genetic variant, so a mutation, which makes you want to smoke, and also which increases your chance of getting lung cancer. But given that genetic variant, it doesn't matter if you smoke or not. And his argument is important because it's that's exactly what we are calling a confounding factor. So of course they had no idea at that time how to what this genetic factor was and how to measure it. It was probably before the DNA was discovered. So that's he pointed definitely out a very important problem that if you just look at correlation, that doesn't imply causation, and you have to be careful and have prior knowledge about other causal influences. And of course it turned out that he was wrong in terms of this analysis. Of course smoking increases your likelihood of getting cancer, and some of these things are influenced by genetic variants, but it's not that a large influence, at least not in this sense. And one possible approach to this confounding problem is to consider them, or to just simply integrate them as inputs, for example, age and gender. Or you just do a separate model for each subgroup. That's called stratification. So do one model for women and for men and for different age groups. And then, of course, the combinations can grow exponentially quickly. So that can be, of course, a problem, but that's a very common approach. So subgrouping the patients in so-called strata. Yeah, so by far the most apparent paradoxes result from unmodeled confounders. So, a lot of these things you read in the newspapers about some research group finding some really odd correlation and implying some causal dependencies is exactly this problem of that they didn't consider all important confounders. Let me recall what the asthma paradox was. I think it was lung disease. So let's say you have like the flu, and which affects your lung functions, of course. And you would assume that if like people with asthma have the flu and people without asthma have the flu, that the outcome for asthma patients might be worse. But it turns out that the outcome for asthma patients after they were treated was better. No, so after they were treated, and so they went to the hospital. Both groups, they got treated, and then you looked at the result, and it turned out the asthma people were healthier. So it looks like a paradox. And the reason it turned out was that if somebody with asthma came into the clinic, the doctors took it extremely serious and gave them very aggressive treatments. Whereas if a healthy person had a flu and came with some coughing to the clinic, they got less drastic medications. So the outcome was then not as expected, but not because there's some strange effect or cross effect between flu and asthma, and it was exactly this type of confounding effect. So I mean, as I said, most of these surprising findings published in the newspapers have such an explanation. And its principle is pretty strong. So if you encounter one of these paradoxes and you think this cannot really be true, if you find the right confounder, it typically gives you a very good explanation of what is really going on. So in personalized medicine, you take even maybe more factors into account. So not just age and gender, but so there's this idea that there's every disease is different, and you should have a very individual treatment for every patient. And so this was the idea of big data in healthcare, and it's still going on, but it turns out not to be as simple as people had hoped for. And a linear model assumes that the effect of an input is on the output is independent of the other inputs. In a log linear model assumes that the effect of an input on the log odds of the output is independent of the other inputs. The idea behind personalized medicine is that a given medication only works for a subclass of the population. So then maybe one approach is to, which also makes healthcare people happy, is to find maybe subgroups. Maybe they first said, okay, it works for men and doesn't work for women, or the other way around. And then they consider maybe age groups and maybe other genetic variants. So you get much more specific about which subgroup of your population is good for this treatment. It's called stratification. And this, the effect, even if the effect is always positive, the degree of effect might be, maybe it works well for young people and not for old people, or the other way around. So this is sort of the idea behind personalized medicine, that you have a finer sort of decision model about what medication to apply when. Of course, you can also do a nonlinear multivariate model like a neural network, but the healthcare people have problems interpreting the predictions and the meaning of these the predictions and how to evaluate it. If you divide your data into strata, or your patients into strata, then maybe if you think about it, you find some good reason why this makes sense. Whereas if a neural network gives you some estimate of the effectiveness of a treatment, you might not have a good intuition why this is doing. And so this is the whole area of explainable AI comes into play. Okay, so this is the end of this discussion, and next we will talk about also a very interesting classifier called the support vector machine, which was brought into play by Vladimir Vapnik, and was sort of one of the main approaches in the time of these kernel approaches. So we will discuss this next. Okay, so let's talk about the optimal separating hyperplane and the support vector machine. The optimal separating hyperplane from Vapnik. Here we consider a linear classifier where the output labels are -1 and 1. It has the property that if classes are linearly separable, the separating plane can in fact be found. So that's similar to the perceptron. And among all solutions for which are valid solutions, we are considering the one that maximizes the so-called margin C, capital C. And what is this margin? So let's consider these the binary classification situation again. So here we have the green examples for the one class and the red ones for the other class. As we discussed with the perceptron, there are of course many linear hyperplanes which would separate these two classes. That's something Vladimir Vapnik thought was not so nice, and he defined the optimal separating hyperplane. So here we're looking at the inputs x1, x2 as the one which sort of has the largest distance to the closest examples of either class. So, and the training data points which sort of define this distance, they're called support vectors. So in this case, it's this, that's the solution. So this is the separating hyperplane which have the largest distance to the closest data points in the two classes, and this distance is called the margin. So this C here. And if you look at this, you could change all these other data points, let's say slightly, and this separating hyperplane, the optimal one would not change, because it's only sensitive to the closest one. And these are then called the support vectors. And so he maybe came up with this idea, and then the question is, how do you formulate this as a mathematical problem or as a mathematical optimization problem? Because you can think of the learning procedure as always an optimization procedure to optimize a particular cost function. So what cost functions gives you exactly this solution? So we want to have a classifier where we look at the sign. So the output is 1 or -1. So we have hard classifier again. And we are considering the linear case, so h is a linear function of the inputs. The following inequality constraints need to be fulfilled at the solution. So y times h should be larger or equal than 1. So remember in the perceptron we had the constraint that this should be larger or equal than 0. And it turns out this makes a big difference, that we insist that it's larger or equals 1. No? So the product, I mean, if this is a negative, of course, then it's not fulfilled. But if they are the same sign, no, then this is not enough. The product should be larger or equal 1. Yeah, so this is just so we have inputs, weights, multiply the inputs by the weights, we sum them up, and then we apply the threshold. And of all possible solutions, one chooses the one that maximizes the margin. So, and this can be achieved by finding the solution where the sum of the squares of the weights is minimal. So of all the w's for which these constraints are fulfilled, we pick the one with where we take the sum over the square of the weights, and we consider the one with the smallest expression here. And again here W naught is missing, although in the model W naught is present. But in this cost function we don't penalize a W naught. No? So this is nothing but a weight decay cost function, if you want. The margin then becomes 1 over the length of the vector at the optimum. And for the support vectors, we have that yi minus times the product of h, I equals 1. And maybe the easiest way to understand what is going on is to look at this figure here. And here we're only considering one input, x, no? and the output y. No? And here are the training targets, or the training data points. So for these three, the target class is 1. For these ones, the target class is -1. And then, of course, we consider just a simple linear function here of one input. And then we can change the slope of this blue discriminant function. And so we can make it sharper. So that we increase the slope. And then we can move it a little bit to the left and a little bit to the right. And in the extreme, we have a lot of movability here. But if we insist that we take the one with the smallest slope, no? And we insist that the values at these data points they must be then larger than 1 or smaller than -1. Under these constraints, we get the solution that at the location where this function changes sign from minus to plus, that exactly is the definition of this the separating hyperplane. In this case, it's a point. So this point has the maximum distance to the class here with a -1 label and the class with the positive labels. Yeah. So if you cannot take a smaller slope, then you would violate this constraint. And if you take a larger slope, then you would have several solutions again. But if you take of the valid solutions the one which has the smallest slope, then that gives you the separating hyperplane. So the optimization problem is now to have the inner product. So this is the weight decay penalty, but without the offset, without the W naught. Under the constraint that 1 minus y times h is smaller or equal 0. And so this is exactly the same constraint as before, just written in a different form. And this is by the way, this was also the time, so this was sort of after the mid-90s and before 2011 in the area of kernel systems. So people also, I mean, you could do some form of gradient solution here, but I mean, inequality constraints are always difficult to handle for gradient-based approaches. Not impossible, but tricky. And so, in other words, we ended up with a pretty complicated optimization problem. So the first part, of course, is not so problematic. We have encountered this already many times. But here we have as many inequality constraints as there are data points. So not as there are parameters, but as there are data points. And this was extremely difficult for the optimization procedures which were available at that time. So they simply hadn't considered this case. They hadn't taken it very seriously because the optimization problems, optimization people who were dealing with didn't have this property. So there was also a sort of a new challenge for people in constraint optimization, and but then very good solution and algorithms were found, and this was made support vectors, optimal hyperplane solutions quite attractive. And I mean, I don't want to go through all the optimization steps, which is relatively complicated and time consuming, and I think doesn't give you much insight because it's only applicable to this particular problem. But in general, maybe that you have you heard of this at least once now, you form the so-called Lagrangian, which is a combination of the term you want to optimize. So for some reasons we put a 1/2 in front. It's really not that important. And then you have a sum over all data points because you have as many constraints, inequality constraints, as you have data points. And then you take this expression here, which should be smaller or equal 0. So that's this one here. And you multiply it by so-called Lagrange multipliers. And then this cost function is minimized with respect to the W and maximized with respect to the Lagrange parameters. So you get minimum in some dimensions and a maximum in other dimensions, and that's called a saddle point solution. So if you have an optimization routine, you have to specify your cost function and your constraints, which end up then in the Lagrangian. And it turns out that the solution can be written as a weighted sum of the data points. So this reminds us of the kernel solution. Remember our discussion on kernels, where this was also our result. And here, this what we called V before is now a product of the target value and this Lagrange multiplier. And the important thing now is that this is also just a sum over the support vectors. And the support vectors are a subset of the training data inputs. And this makes sort of the solution somewhat more efficient, because in most optimization cases you have to consider all data points, and here you only have to, at least if you're close to the optimal solution, only the support vectors appear, and this might be a very much smaller set than the complete set of training data. So we can write the solution essentially in kernel form. So in the simplest case, this kernel is the inner product of these inputs. But of course, we can also use a kernel representation where we're working in some feature space. So the solution, because of this property here, can be written as a sum of these the kernels. And here, instead of the v's, we're writing the targets. So 1 minus 1 times the Lagrange multiplier. But that's just maybe a little bit detailed. So this principle of optimal separating hyperplane, when you do the optimization, immediately also leads to a kernel solution. And in fact, the story is that Vapnik first only considered the linearly separating hyperplanes, and he came up with this particular cost functions, and people thought weren't really interested in another linear classifier, and the excitement only started when these kernel solutions were derived, and then these support vector machines, how they're called. So the support vector machine are these optimally separating hyperplanes in combination with kernel approaches. They got pretty good results, or very good results, very quickly. And sort of the neural networks people, which were sort of their competitors, had at that time had a hard time beating them. In fact, for many problems, if the number of data points you're having is not too large, let's say 20,000 or something, support vector machine can be quite competitive to deep neural networks or neural networks in general. So it's not that they are completely not used anymore. They're still being used, and sometimes they give extremely good results still, but they are sort of limited in terms of the number of data points, as any kernel approach. So, and then people were not so happy or criticized the support vector machine because the assumption was that the classes are linearly separable. So, I mean, if you work with kernels, this is not completely unreasonable, but still people complain that often classes overlap, and this approach didn't seem to consider that. And the solution came with the so-called slack variables, psi I. So again, we are trying to find the weights which minimize this expression here, the one we've used before. But now we are relaxing the constraint a little bit. So y times hi, before we said it should be larger or equal 1. Now we are saying it's larger or equal 1 minus psi I. And the psi I are positive. And in principle, we can have 1 psi I for every data point. So the psi I should be non-negative, and the sum should be smaller than 1 over gamma, where gamma is a parameter to pick. So the larger this gamma is, the more slack is, the smaller lambda is, gamma is, the more slack is permitted. And again, for gamma towards infinite, then this becomes 0, and we don't allow any slack. This is how it is mathematically formulated. Again, it's an optimization problem with inequality constraints, and this is the geometric interpretation of what is going on. So this would be a data point which is within the margin, which would not have been allowed in the original formulation of the support vector machine. Here's another one, and this one is even on the wrong side of the class, and even on the outside of the margin. So, and these this is what these size are. No? They are they tell you how much this constraint is violated. And it turns out all these guys also then become support vectors in the sense that they appear in the final solution. So there are different ways of solving this problem with the slack variables. One way is to write this cost function in this form. So here we have the weight penalty again, and we're looking for the solution which minimizes this expression. Here's the 2 times the gamma, and the sum over the function on 1 minus yi times hi, and this function is 0 or so the maximum. So if the argument is positive, then it's the argument. If the argument is negative, then it's 0. So you can write this concept also in this form, and this gives you a little bit more intuition of what is going on. So if so you're penalizing this expression, but it's easier to look at by comparing the different cost function terms. So we are considering a data point of class 1. And so the target is 1, and the contribution of one data point to the cost function for different cost functions. So the simplest one is the least squares, which is then simply 1 minus hi squared. So that's this one. So we have the target is 1, and if the prediction is not 1 at this location, we get a quadratic penalty, and we get it if it's larger than 1, which should not really be a problem, and we get a penalty when it's smaller than 1, which you might think this is reasonable. So this is this contribution if we have this squared cost function here. Then we have the perceptron, which is the black curve, which is this one here. So if h is larger than 0, then this data point sort of disappears from the cost function, and the contribution is a constant 0 here. But if the sign is sort of incorrect, so in this case negative, then we get a linear penalty. So you can also see here if the system will feel this data point here, and then the moment it becomes positive or not negative, we don't care anymore. No? So this is the typical property of the perceptron. And then Wapnick's optimal hyperplane is the green one. So it's very similar to the perceptron cost function, but it's shifted to the right. So it means even if the sign of h is correct, we are still not happy. We want it to be larger than 1. And only then the cost disappears. The cost term disappears. And then we consider logistic regression, which is magenta. That's this curve. So in a way, it's a soft form of of Wapnick's cost function. No? So if it's very negative, very incorrect, then it becomes also sort of a linear term, and then if it's already correct and maybe even 1, it still wants to push it towards larger values, and then never disappears. Not only when you have this behavior that the cost function becomes insensitive to this data point, you have this effect of a support vector, no? That the other data points which are not support vectors really disappear from the cost function. But it's not, I mean, it has some common properties with Wapnick's cost function. And then finally we have the neural network, which is this one here. Now, which so this was the classical neural network cost function. Now, where we take y minus sigmoid to the square, and that has this. I mean, on the right side, it looks very much like the logistic cost function, but then here on the left side, you see that the gradient becomes 0 if you're extremely incorrect. So it has this strange behavior. If you're really incorrect, then the cost function doesn't care anymore. And that's why this particular old neural network cost function is really not that used that much anymore. Now we're considering a few toy examples from Trevor Hasty's book. So we have two classes, red and green. Classes overlap. The true class boundary is in violet. The continuous line is a separating hyperplane found by a linear support vector machine. So a linear support vector machine is the same thing as an optimal separating hyperplane approach. And all data points within the dotted regions are support vectors. So that's 62% of all data points. And gamma is large, so a little slack is permitted. So this is sort of more or less, I mean, we have overlapping classes, but still we try to avoid, I mean, we don't give much slack. So here are the data points, green and red. We've seen this example before. This is the optimal solution. Of course, we are limited because we are just assuming a linear dependency, and this is what is found. And all these data points, I mean, all the ones on the incorrect boundary are support vectors. So all these green guys here, everything which is within the margin, they're all support vectors. So that's why we have so many support vectors. No? Here's the test error, 0.288. Gamma is very large. So then linear SVM with a small gamma. We even have more support vectors, 85%, and the test error is almost the same. It's a little bit worse. But we are seeing if we allow more slack, we even get more support vectors. Then with polynomial kernels, the test error is reduced since the fit is better. And the support vectors are close in the separating hyperplane, but this is in high dimension, so we have to now look at the support vectors in the original input space. So this is what the polynomial classifier found. So the error went down drastically. No. And this is the so it shows you where the margin is, no? And then we also see the support vectors, which are the points within the margin. And yeah, the fit is not bad, no? In the areas where there's enough data to give you some understanding. But then, no, of course, we are sort of looking back from high dimensions to low dimensions. We also get support vectors in unexpected regions, which in this two-dimensional plot look like they're very far away from the separating plane here. Or, of course, it's a separating hyperplanar manifold. But it's just because we're looking at this low-dimensional projection. No? And then they use Gaussian kernels, and I think the error went down even further, so 0.245, 0.218. So the Gaussian kernels, they have nice properties and give you good results in this situation, because we have highly complex boundaries, and then Gaussian kernels or RBF kernels are pretty good. Yeah, and the idea of searching for solutions with a large margin has been extended to many other problems. So there's a whole family of cost functions derived from this margin problem. And then finally, I also want to compare a little bit the separating hyperplane, optimal separating hyperplane with the perceptron. So the main difference is in the perceptron we said this product should be non-negative, and here in Wapnick's approach, it says it should be larger or equal to 1. So this is a support vector machine. We have seen this before. It's very stable. It's very well defined. It's convex. There's only one solution, which is also nice, which made it very popular. No? In neural networks, it was criticized that we had multiple solutions and all these problems. Support vector machine is like a kernel approach with a unique solution. So that's very nice. But if you look what the perceptron is doing, it might be classifying these data points correctly, because it's only interested in that the sign is correct, and even this very flat curve, and in the limit the sign might even go, the slope might even go to 0. The training error is still 0, so the perceptron is happy. But you sort of already see that this is pretty unstable, and if you change the parameter values just slightly, it might give you extremely incorrect classifications. So this sort of constraints that y times h must be larger or equal to 1 gives you much better and stable solutions, and also gives you unique solutions. No? It doesn't have this ambiguity problem of the perceptron. Okay, thank you very much.